Now that we have an understanding of how power functions behave, we're going to start looking at a different kind of functions called polynomials. And in particular, we're going to look at their end behavior as well. So first, we're going to define what polynomials are. We're going to introduce some terminology that'll make it a little easier to talk about polynomials. And then we're going to introduce some methods for looking at the end behavior of polynomials. And we're going to apply these methods to an example. So in general, a polynomial is a function whose actions rely on only addition, subtraction, and multiplication. And if you want to see what a formula for that looks like, it looks like that. So the function has the formula f of x equals constant plus constant times x plus constant times x squared all the way to constant times x to the n, where n is some highest power of x that you have in the formula. And again, each of the ai's is going to be a constant. So as an example, you could have f of x equals x squared minus x plus 7. It's not written in exactly the same order as the polynomial above. If I did want to write it that way, I would write it as 7 plus negative 1 times x plus 1 times x squared. Still a polynomial. It doesn't matter what order that you write the terms. Here's another one that doesn't look very polynomial-y. It's a linear function, but it is a polynomial because you could think of that as the constant 2 plus 3 times the constant x to the 1. So x is the same as x to the 1. And here's another super boring polynomial. That's just f of x equals 2. That's a constant polynomial. You could think of that as 2 times x to the 0. So the highest power of x is x to the 0. Because remember, x to the 0, any number to the 0 is equal to 1. Alright, so again, here's the definition of what a polynomial means. We're going to introduce some terminology that'll help us talk about polynomials in a less clunky way. So first of all, one of the things that's going to be important to us is what's called the leading term. And the leading term in the formula above is just a and x to the n. And what distinguishes that from the other terms is it's the one with the highest exponent of x. Right, so you go to the highest exponent of x, that term is your leading term. Your leading coefficient, that would be an, and what's important about that is that's the coefficient for the leading term, for the term that has the highest exponent of x. And then the other one is the degree of f. Now that is going to be n, and what is important about n is that is the actual exponent in the leading term. So n is the highest exponent of x that you have in the formula for the polynomial. So as an example, if we're looking at f of x equals x squared minus x plus 7, there our leading term, that is the term with the highest power of x, that's just going to be x squared. The leading coefficient, you can't exactly see it there, but remember, another way of writing x squared is 1 times x squared, so the leading coefficient is actually 1. And then if we're looking for the degree, that is the highest power of x in the formula for the polynomial, and that comes again from x squared, and that exponent is 2. So for the linear function, f of x equals 2 plus 3x, there our highest power of x is x to the 1, so our leading term is going to be that 3x. The leading coefficient is going to be the coefficient from that leading term, that's just the 3. And if you want the degree, that is the highest power of x. The highest power of x is the only power of x in that one, that is x to the 1, so our degree is 1. And finally, for our super boring polynomial, our constant polynomial, it still has all these things going for it. It has a leading term. Well, it only has one term, so that's the leading term, 2. The leading coefficient, that is also 2. And then the degree might not be obvious, except again, if you want to think of 2 as being 2x to the 0, which of course we can, because x to the 0 is equal to 1, then the highest power of x that you have is 0. So our degree is 0. Alright, so let's start looking at end behavior of some polynomials, and we're just going to look at an example. But just to remind you of what end behavior is, that's what happens to the outputs of the function as x gets really big and positive, or really big and negative. Alright, so here's an example. F of x equals negative 2 times x squared plus 3x plus 100. And of course, one of the ways that we can at least make guesses about what the end behavior is going to be like is to look at the graph. So here's what the graph looks like. Not surprising, we know the graph is a parabola, and because it has a negative 2 in front of that x squared, that means it's a parabola that opens down. And if we're looking at what the end behavior is, or what we think it is based upon the graph, it looks like as x goes to infinity, as we head to the right of the graph, then we start going way down. That appears that f of x goes to negative infinity. And as x goes to negative infinity, f of x still looks like it's going to negative infinity. And the question is, how do we determine that analytically? Well, if you look at it, I mean, the function appears to behave just like g of x equals negative x squared, right? That's a power function that we understand pretty well. We understand what the end behavior is on that. And it looks like the end behavior for our polynomial of degree 2 is going to be exactly the same as just plain old negative x squared. So the question is, how can we make that connection between our function and negative x squared? Well, one way of doing that is simply to factor out an x squared from each of the terms and see what's left over. That doesn't seem super intuitive, because it's looked like for at least 2 of those terms we're going to have trouble factoring out x squared. But let's give it a go and see what happens. So f of x equals, well, let me see. If I'm factoring out an x squared, that means I'm factoring out x squared from each individual term. Now the first one's not so bad. That's negative 2 times x squared. When I factor an x squared out, we just get negative 2. That 3x is a little tricky though, because it doesn't look like we have 2 factors of x to factor out of 3x. We just have 1 factor of x. But we can play a little algebraic trick by writing 3 over x, and then when we multiply that by x squared, one of the x's cancels, and that just leaves us with 1 factor of x. We don't have to do this, factor this in a way that leaves everything without fractions. We just have to factor it in a way that gives us the same same expression as we had before. And we can play that same game with 100. If we factor out 100 over x squared, then that will work out as well. And just in case you don't believe me, let's go ahead and check that out. So let's take that x squared times negative 2 plus 3x plus 100 over x squared and see what happens when we multiply everything out. Hopefully we'll get the original function back. Well, I'm just going to go ahead and distribute that x squared through the entire sum. So that's x squared times negative 2 plus x squared times 3 over x plus x squared times 100 over x squared. If I want to clean up that first term, that's just negative 2 times x squared. We're not too shocked about that. In the second term, one of those x's is going to cancel because of that x in the denominator, and that leaves us with just 1 factor of x times 3, which gives us 3x. And then both factors of x are going to cancel in that last term, leaving us with just 100, and that's exactly what we had at the beginning. So here is our factored form of f of x, not a factored form that we usually think of as our normal factored form, but that's what it is. And yeah, it looks like a mess. Try not to criticize, but it turns out to be a super useful mess. Because as we let x goes to infinity, it's going to be a lot easier for us to analyze. So what's going to happen? Well, let's see. I want to look at that 3 over x, because I want to sort of analyze what's happening to that as x goes to infinity. Well, think about it. That 3 is just a 3 in the numerator. Not anything too exciting. But that denominator is x. And remember, x is headed towards infinity. That means x is getting huge. So that 3 over x is going to be 3 divided by a huge number. And if you want to try to use your quantitative imagination with 3, this little teeny tiny little 3 divided by a huge number like a billion, a trillion, a quadrillion, it's going to be a teeny tiny number very close to 0. And so as x goes to infinity, 3 over x is headed towards 0. 100 and x squared over x squared, same thing. 100 may seem like a big number, but again, that x, it can be any number of any size. It can be huge. Again, a billion, a trillion, quadrillion, quintillion. When we square it, it's even bigger. So we get 100, which is a relatively puny number divided by a huge number. That one's headed to 0 too. So that enables us to figure out what's happening with f of x. So let me see. So again, it's equal to x squared times the quantity negative 2 plus 3 over x plus 100 over x squared. Let's look at what each of those is doing as x goes to infinity. Well, that x squared, that's a huge number, and you're squaring it, that's headed towards infinity. That negative 2 is just headed towards negative 2, and as we've seen, those other two terms are headed towards 0. So you get infinity times negative 2 plus 0 plus 0. That's where we're headed towards as x goes to infinity. So what that's saying is it's heading towards a number that is huge times a number that is close to negative 2. A number close to negative 2 times a huge number gives you a huge negative number. So that's headed towards negative infinity. Exactly what we saw in the graph. All right, so let's try to use the same reasoning to see what happens as x goes to negative infinity. Well, we're going to do the exact same thing. Look at what 3 over x is. X goes to infinity, x goes to negative infinity. It's going to give us the same result. 3 over x is still going to 0. 3 over a billion, 3 over a trillion, that was very close to 0. If we put a negative in front of that billion, trillion, it's still going to be a number. It's still going to be a number close to 0, just on the negative side. So still 3 over x is heading towards 0. And again, 100 over x squared, also heading towards 0. And so if we want to analyze what's happening to this as x goes to negative infinity, remember that x squared as x goes to negative infinity, you're squaring that negative number. That's going to give you a positive infinity for x squared. The other ones behave exactly the same as when x was going to positive infinity. You get negative 2 plus 0 plus 0. So once again, you're getting a huge number times a number that is very close to negative 2, and that is going to give you a negative huge number. So your end behavior is going to be going towards negative infinity. So I hope this sort of gives you some thinking to do about what we mean when we talk about simplifying expressions. Because in the old days, in your algebra classes, there were probably certain rules about this is how you make an expression as simple as possible. But I want to expand the way you think about simplifying expressions. So first of all, I want you to understand that a simplified expression, that's a subjective term. I'm expressing an opinion of what I think is simple and pretty for an expression. And my opinion and your opinion may be different, and that's totally okay. And when we say that in our full generalities, we usually mean as simple looking as possible, but I'd like to think of it a little bit more practically and think of it as useful as possible. Sometimes it's useful for an expression to look simple, but as we've seen, there are some expressions that don't look so simple that are much more useful for different types of problems. So what I want you to think about is when you're simplifying an expression, you should simplify it in a way that is useful for the problem that you're working on, not necessarily what's useful in the way that you're used to thinking of it in terms of being pretty. All right, so now that you've thought about that for a while, I think you're ready to work on the in-class activities. The file is called Polynomial End Behavior.